Yeah. Yeah, whatever. All right, everybody. Let's get started. Hope lunch was good. Okay, so our next speaker for today is Alon. Uri is a research scientist at Google. Prior to that, he was a postdoc at CMU with Graham Neubig. Prior to that, he did his PhD at the Technion with Aaron Yahav. He's thought about generalization in many contexts. So he's thought about kind of generalization across longer contexts, generalization in the settings of code, in-context learning, and today he'll tell us about in-context principal learning from mistakes. Let's welcome Uri.
Thank you, Andre. Hi, everyone. Thank you for joining, and thank you, Andre, for inviting me. So as Andre said, I'm a research scientist at Google DeepMind, but this work was mostly done by Tianjun Zhang, who recently graduated from here, from UC Berkeley, and also Aman Madan and Luo Gao, who graduated recently from Carnegie Mellon University. And this talk is about in-context principal learning from mistakes. So let's start with a story. When I was an undergrad, that's me as an undergrad, I hope I didn't change much. I had a teaching assistant who had a unique way of teaching us how to solve problems in calculus. First, he would present us with the wrong solution, discuss why it is wrong and how to avoid such pitfalls in the future. And only then, he would show us the correct solution and how to really solve the problem. Now, for us, for us students, it was a really useful way of learning, because by looking at the wrong solution and the correct solution side by side, we could gain a little extra learning of what the problem is about and how to avoid mistakes in the future, which is slightly more than just seeing, a teaching assistant solves the problem correctly, and that's it.
Best of it.
What?
This is best of it. It's good.
Not exactly best of it, but let's discuss that later. So with this motivation in mind, we wanted to see if we can teach LLMs to leverage wrong solutions when we know that they are the wrong solutions. So specifically, the kind of questions we were interested in were reasoning questions, similar to the questions from the GSM 8K benchmark, such as the bakers at the Beverly Hills Bakery baked 200 loaves of bread. Some were sold, some were returned. And the question is, eventually, how many loaves of bread did they have left by the end of the day? The standard way these days of approaching such problems is to provide the model with a few-shot examples. Also, this approach is called in-context learning or few-shot prompting, where we provide the model in the test context with similar or questions in the same domain or in the same general area. So, for example, our prompt example in this case is Roger has 5 tennis balls. He buys 2 more cans of tennis balls, blah, blah, blah. How many tennis balls does he have now? And we provide the model with the answer to that question, to the prompt question. And more importantly, not only that we provide the model with the final answer to that question, to the prompt question, we also, the common approach these days is to provide the model with the entire chain of thought, or the entire solution step by step, decomposed into steps, hoping that at test time, and in practice it works really well, hoping that at test time the model will be able to apply a similar or a similar in spirit decomposition of the test question and arrive at a better solution to the test question as well. And this in practice works amazingly well, and that's the standard approach of addressing maybe the first baseline that everyone should use when addressing such problems. So notice that even though this few-shot prompting with chain of thought is so popular, it uses only positive examples. We only provide the model with questions and the correct way of solving them. And machine learning has always been about positive and negative examples. since the perceptrons and since the 1950s and models like perceptrons and support vector machines, machine learning was always about positive and negative examples and learning the contrast between them or the difference between them. So our question was, how can we leverage negative examples in context learning, which currently uses only positive examples? So our first attempt was to just include negative examples in the prompt. So we started with this vanilla prompt template of the standard chain of thought few-shot prompting. And we added a wrong solution to the same question and explicitly told the model, hey, this is a wrong solution. So for example, the wrong solution in this case is Roger has 5 tennis balls plus 2 cans of tennis balls. 5 plus 2 equals 7. And obviously it's wrong because you can't add balls and cans. And then the correct solution as before. And we hope that for the test question that we really care about, the model will be able to repeat this process of suggesting a wrong solution and then suggesting a different, we hope that it will be a different correct solution that at least covers or at least avoids one possible mistakes that the model had already covered by suggesting a wrong solution. It turned out that this either doesn't work or that the effort in manually creating the negative examples could be better used by manually creating more positive examples. So eventually, this approach didn't make the results overall better. Yeah. You mean presenting the correct solution and then the wrong solution?
Because at that test time you just want to just generate.
I think that we tried it, but that was, I think that was in our initial experiment, that was even worse. Because then the model at test time did not have the opportunity to kind of sketch a wrong solution to the test question as well, because it kind of learned to follow the pattern of question, correct solution, and then wrong solution. So it didn't have the opportunity to make a mistake and learn from it. At least that's what we found in really initial experiments. Yeah.
Does this somehow not depend on how you create the negative examples? Like if I tell you 2 plus 3 is not 3 million, it's presumably less useful than if I tell you 2 plus 3 is not.
Yeah, I agree. There's kind of an infinite space of like possible mistakes that you can make. I agree. We try to make the mistakes similar in spirit to the mistakes that we observed the model to usually do. So potentially we could have created different wrong examples that would have changed the results, but we tried to make them kind of natural to the model.
In that case, is what you're doing. I mean, you haven't told us yet what your solution is. I have some guesses what it might be, but it sounds like it might be similar in spirit to RLHF, where you also have the model generate pairs of answers, and you say, hey, you do this one and not that one.
Yeah. So in this work, we did only prompting.
Sure. And you're going to have it generate a solution and then decide whether it's right or wrong.
Something like that. I'll talk about it in one of the next few slides. But it's a good point. In this work, we only focused on prompting. I do believe that further training using approaches such as RLHF can possibly work better, although they have their disadvantages as well. They consume much more compute and so on. I'm thinking whether to say that now or later. I think about this work as kind of in-context RLHF, something like RLHF that is learned at prompting time, completely in context. Okay, so yeah.
Understand the analogy between like positive and negative examples, like, but like in that is like actually more of like learning 2 classes. Like it's not like they're actually like one is correct and wrong class. It's more like 2 different classes. I could have called it, I don't know, flowers and plants or whatever if I wanted, right? Like they're just 2 different classes. They're not necessarily like wrong label, right? I'm trying to understand the
Right. I agree that the analogy to like classical machine learning, where is not like 100% accurate, where as you say, in classical machine learning, we had two distinct classes, and here in our case, it's unclear what is the class anyway, right? A language model is basically doing classification over the next word. So by saying that we are classifying correct and negative solutions, it's not. I agree that it's not 100% accurate. My point is that we had an intuition that there is something to learn from negative examples, similarly to how the calculus teaching assistant was showing us negative examples before showing us the correct solution. We felt that there is some signal in incorrect solutions. If you know that the solution is incorrect, there is some signal that that you can learn from, or at least one possible path not to take. But I agree that the analogy is just a hand wavy analogy to support vector machines, not completely accurate. So our next attempt was to ask the model to provide the negative examples, because we didn't want to put effort into creating negative examples. So we just took this few shot chain of thought template and asked the model to first generate a wrong solution to the above question, then explain why the solution is wrong and how to avoid it, and finally generate a correct solution. This way, we hope that the model will be able to come up with the wrong solution, discuss it on its own, and provide a correct solution without any effort from our side. However, this turned out to also not work, and the model often generated a correct solution as the wrong solution, and then fixed the correct solution by breaking the correct solution and eventually providing a final answer which is wrong. And the final accuracy over the entire test set was eventually slightly lower. Our third attempt was actually chronologically a paper that Aman, one of the authors, has led last year, which is called Self-Refine, where the idea is to provide the model with the initial question or input, then pass the model's initial answer to the same model, just with a different prompt that encourages the model to give feedback on its own initial answer, and then take the feedback and the initial answer and feed it to the same model with a different prompt that teaches the model how to refine previous answers, and this way get a refined answer, and we can repeat this process several times until we run out of a predefined budget, or until the final answer doesn't change. That's a heuristic that is up to us. However, it turned out that self-refine, while working for more open-ended tasks, does not work for reasoning tasks, because the model cannot identify incorrect solutions without any ground truth validator or any external signal or unit test or anything like that. The model has no idea if its initial answer was correct or not, and thus cannot provide any additional improvement for reasoning tasks. And this was observed in a paper from last year called Large Language Models Cannot Self-Correct Reasoning Yet. In that paper, they found that specifically for the GSM 8K benchmark using GPT 3.5, the majority of the answers did not change following this self-refinement loop. And the number of cases where an initial correct answer was turned by the self-refinement loop to an incorrect answer was greater than the number of cases where that we kind of wished for, that an initially incorrect answer would become a correct answer. So overall, the final accuracy on the entire test set either didn't change or decreased. So the conclusion here was that test time self-correction does not improve reasoning unless we have some kind of an external signal that can tell us whether the answer is correct or not. And this led us, yeah, was there any question? Okay, so yeah.
So you can take the correct to correct as a signal for basically kind of, so if the answers are deterministic, And then if you go from one correct reasoning path to another, basically if they're self-consistent in a sense, you can take that self-consistency as even more signal for being correct.
You're saying that we should take these green cases. Oh, sorry, the orange, the blue cases.
Right? So they give you fairer signal that this is probably just correct. If you go from the same answer to the same answer. Right?
So it gives you a signal that it's correct, but what do you do with that signal? Like, how can you leverage it to improve the overall?
Saying that you don't know if your reasoning was correct or not. I'm saying so that the correct to correct kind of it is giving you a signal that it's probably correct. Meaning that if you're arriving at the same solution, in a sense, if it's self-consistent, that's
No, that doesn't mean so. It can be confused and it stays confused.
but that incorrect to incorrect is like 9%.
But producing this pie chart can be done only if you have the label. So correct to correct means that you know that the final label is correct. So
But even without knowing, it's like now, in hindsight, 75% of cases that were self-consistent were correct. So that signal that basically staying self-consistent is likely correlated with, highly correlated with.
in general, yes, but these incorrect to incorrect are also consistent, right? Or
We can take it off.
okay.
Yeah. Let me just rephrase it as a question. Of that blue region, does the brown region that says incorrect to incorrect also include all the cases where the incorrect solution was not changed, or were those only in the blue region? So like, you could divide that blue region into those that are correct and those that are, stay correct, and those that are incorrect and stay incorrect.
Why? I think that if the answer was incorrect and then stayed incorrect, either it stayed the same or was incorrect in another way, it was counted as in the brown region.
So the blue region is all correct to correct.
Yes.
And there were almost no correct to correct that changed the correct answer.
You mean the initial answer was correct, the final answer was correct, just in a different way? I'm not sure. I don't think that this is from the large language models cannot self-correct reasoning yet paper. I believe that they did not did an exact string match between the initial and the final answer. They just checked whether the final answer is the same. So it's possible that the blue region contains cases where the solution stayed correct, even though in a different way. Although in those benchmarks, it's there's usually one way of being correct. So I can't imagine a case where the model reaches the correct answer in a completely different way.
Answer is a number. The answer is a single number.
So you're just checking the number, you're not checking the reasoning being the same?
Right.
Okay.
That's usually what people do, yeah. Just because it's too difficult in these kinds of questions to check the entire reasoning, but it's much easier to see if the final answer is correct or not. You can prompt the model to surround the final answer with curly brackets or something like that, and then you just extract the final answer and check if yeah. So this led us to the fourth approach, which is the approach that we propose in this paper called a leap for learning principles. And the idea is as follows. Recall that we have a few labeled examples. This can be as few as 3. And for these examples, we have both the question and the answer, the ground truth answer that we have it labeled. And we also have a large test set of questions only that we don't have the answer for. The approach is as follows. We start with these few labeled examples, And we kind of learn in context, we have an additional sort of training step, which does not involve any gradients or anything like that. But I call it the principal learning step. And everything is happening here in context. Let me show you what I mean. We take each of these labeled examples, pass them into the LLM in a zero-shot fashion, just provide the model with the question and ask it to solve the problem step by step. And we can sample a variety of possible answers using non-zero temperature. And because this is one of the labeled examples, we have the ground truth label. So we can know which of these sampled answers are correct and filter them out, and which of these sampled answers are incorrect and keep them. So we keep only the wrong solutions, and then we craft a prompt as follows. We provide the model with the question, the generated answer, which we tell the model that is incorrect, the correct answer, and an instruction in the spirit of explain why the generated answer is wrong and what principle should you use to avoid this mistake in the future. We feed this prompt to the LLM and get a principle or a lesson. And notice that this principle does not contain the answer to the question. So the hope is that this principle or lesson would be general because it doesn't contain the answer. It just kind of contains the difference or the logical step that you need to take in order to go from the generated answer to the correct answer. So we hope that since this lesson only has the small difference or the small mistake to avoid, it would generalize better than providing explicit examples and hopefully generalize to other examples as well. I'll show some examples in a few slides to make it more concrete. So we started with a few labeled examples. There's few of the three. We passed the question to the LLM, sampled a variety of answers, kept only the wrong ones, then crafted a prompt composed of the question, the answer, and the correct, the ground truth answer, fed that to the LLM to get a principle. And notice that the important part here is that we have a prompt that is composed of the question, the generated answer, and the ground truth answer. So by showing the model the generated answer and the ground truth answer side by side, we hope that this could mimic the original motivation of the calculus teacher who showed us the correct solution and the incorrect solution side by side. And I think that looking at the correct solution and the incorrect solution side by side is a step that the model never experiences in standard prompting approaches. Yes, please.
Correct it? Like, is that also given? Like in the previous slide, you had the instruction, this part, like that explaining why the answer is wrong. Is it also something that you generate from LLM, or is it somebody writing those prompts? Or
we asked the model to generate this explanation. We didn't have any additional supervision or any additional labeling other than the original test set. So these test sets usually come with a few labeled examples. These labels contain both the step-by-step solution and the final answer. We didn't do any additional labeling besides that. We wanted to be kind of completely fair in terms of the manual effort that is required. So we did ask the model to explain why the generated answer is wrong. Sometimes the explanation was correct, sometimes it was incorrect. We hoped. Not always, yeah. It's not always super important if the explanation is correct or not. The important thing is to tell the model that this is the correct answer and this is not. Without that, the model can't learn anything. That's basically by telling the model that this is the correct answer and this is the incorrect answer. That's basically the supervision that the model gets that allows it to learn the principle.
Thank you.
So just to recap, we started with a few labeled examples. We fed. We saw this slide. Okay, so we started with a few labeled examples. We generated a principle or a lesson from each labeled examples. And the more few-shot labeled examples we have, the more lessons we can learn. and sometimes more than one, because from the same labeled example, we can make a variety of different mistakes and then learn a variety of different principles from them. And overall, we get a set of principles that we called low-level principles, because they were learned directly from the pair of incorrect and correct answers. We also had an optional additional step that sometimes helped and sometimes didn't. We can discuss later why we believe that it helps and why it doesn't help. But the second step was learning more high-level principles, and it worked as follows. We took the entire set of principles that we learned, concatenated them one after the other, and asked the LLM to summarize, deduplicate, abstract, and generalize them into 8 high-level principles. So just a sec. So we fed this prompt to the LLM, and we called the outcome high-level principles. So notice that the high-level principles are generated by looking at the entire set of low-level principles, but each individual low-level principle is generated by looking only at one correct and incorrect answers. These low-level principles never see the entire other set of low-level principles, so there might be repetitions between the different low-level principles. Yes, please.
What is an example of a principle?
Yeah, I show that in one of the next slides. I know that that's the main thing that you're curious about now. So just to recap, we started with a few labeled examples and a large test set of questions only without answers. But now, using the same budget of data and same budget of supervision, we didn't have any additional data or any additional supervision. We also have principles that are specific to this task or to this domain. So it's kind of like learning these principles, which is the entire process that I described in the past few slides, is kind of like learning a new prompt that is specific to these to this domain, and but it's basically for free. We didn't spend any additional data. The only cost is a few more queries to the LLM. But this can be done once for each domain or one for a test set. So the cost is constant, something like 30 API calls if we think about the LLM as a kind of a cloud LLM that we send queries to. It's a constant cost of something like 30 API calls, and then we can use the same principles over and over when we solve the rest of the test set. And the final step of actually kind of solving the test set or providing answer to the test set is that we take the test question, which we don't have an answer for. We prepend our few-shot examples. That's the standard way of the baseline few-shot chain of thought. The only difference is that in our case, we also have either the low-level or the high-level principles to prepend as well. And we finally, for each test question, we feed this prompt to the LLM and get the final answer, which we actually measure for reporting the final accuracy of this LLM. Here are some of the results. I'll go over them briefly to go faster and get faster to the examples of the learned principles. As you can see, we have the orange bars, which is the baseline few-shot chain of thought, and the two blue bars are either the low-level principles or the high-level principles. We evaluated this on more than 20 benchmarks using all the latest LLMs like GPT-4, Gemini, GPT 3.5, Claude, and these are some of the results. The full results are in the paper. As you can see, sometimes the high-level principles worked better than the low-level. Sometimes the low-level worked better than the high-level. It was mostly consistent with the task, not with the LLM. So, for example, if in the drop benchmark, GPT-4 worked better with low-level principles than with high-level principles, the same trend usually occurred for the drop benchmark, even with other LLMs. And yeah.
Use the few shot examples, first principles, and then few shot examples, and then you generate, right?
Yes.
Now, my question is, what if you drop the few shot examples and just stick to the principles? Does that work out?
Yeah, so it's a great question. So the question was, what if we drop the few shot examples and keep only the learned principles and the test question? We tried that. We have these results in the paper. The question is, what should we compare this to? Because the results were lower. But the question is, what's the baseline?
No few shot at all. So then how much improvement will you get?
So if we take only the principles and the test question without the few shot examples and compare it to zero shot, it's better. Our approach with the principles is better. But on the other hand, it might not be a fair comparison, because in order to generate these principles, we had to have 3 labeled examples. So we kind of indirectly had these few shot examples in mind when we created the principles. The principles kind of compress these 3 examples into another form, into the form of principles. So comparing that to zero shot might not be a fair comparison.
Okay, I'll check out.
Okay, we got to the interesting part of what are those learned principles. So here are some of them in the GSM-8K benchmark. One of the principles was when solving a problem involving multiple sources of income and expenses, it is crucial to keep track of each component separately and calculate the total accuracy, which makes sense. In math, when simplifying complex numbers raised to powers, it is important to remember the following rules about imaginary numbers, that I squared equals -1 and so on. And interestingly, notice that you might think that, why do we have to learn this principle? Because if the model had generated this principle about the imaginary numbers, it means that the knowledge about what are imaginary numbers and how to calculate them are there somewhere in the model's weights. They are there. So why do we need to have like this? You might say that this principle does not provide us with any new information. All the information was already buried in the model's weights. So why do we need this? And I don't have a good answer. My hand-wavy answer or intuition is that similarly to how the model has these imaginary numbers kind of rules in its weights, it still made mistakes. To generate this, the fact that this principle was learned means that in one of the samples in the principal learning step, a wrong solution, the model has generated the wrong solution. So even though the model has the rules, the imaginary number rules in its weights, it can still sometimes use them incorrectly. So my hand-wavy explanation is that by having these explicit principles in the prompt allows the model to kind of prefetch them or cache them to have them more handy and use them more easily when solving a problem that involves in imaginary numbers. So I would love to hear your thoughts, but that's at least my explanation. Yes, please.
Is there a cutoff for the negative examples, like in terms of the likelihood? Like, do you have any of the, like, are any of the negative examples such that the likelihood of the model is actually very low for the answer?
We didn't experiment with that at all.
Like, it's possible that it made a mistake because you somehow like ended up pulling from something that the model actually assigns a pretty low likelihood, depending on how many times, I guess, you resample to get the negative examples.
Right. You're saying that you're basically saying that the negative examples that we generated might be kind of artificially negative because we sampled with a non-negative temperature, so they might not be generated naturally. Yeah, that's a valid point, and we kind of in the principal learning step, we kind of forcing the model to make mistakes. It might not be mistakes that the model would have made in greedy, decoding. We're kind of forcing the model to make mistakes, only to fix them later. Yeah. Yes, please.
Yeah, what's a good principle, what's not a good principle?
We didn't do any judging. We just took the set of principles that were produced, and with no judgment. If we had a judgment, it would obviously be better principles, but we didn't want to introduce another source of any supervision or labeling.
But when you look at them, they seem to be very similar, but you don't know whether there are other good principles that haven't been fished out.
Right. Right. They all look reasonable. Some look more helpful than others. Yeah, I agree that potentially if we had another set of like three, every benchmark is supplied with a limited set of few-shot examples. So it's possible that if three other random examples were provided as the few-shot examples, the resulting principles would have been completely different.
I think it would be very interesting, make it longer and change the few shots and see how consistent these principles are.
When you change the source, like the seed examples,
yeah,
they are actually very inconsistent. The low-level principles are usually more specific to the exact mistake that that was made in regards to the few labeled examples. That and the point that you raise was kind of the motivation to introduce these high-level principles, to kind of try to generalize them to get principles that cover more cases or would be applicable to more test examples. But yeah, the seed few-shot examples basically determine the resulting principles.
And the high-level ones are more consistent.
Slightly more, but also not consistent. Different examples would lead to different principles in general.
Yeah. Is it possible to go to the accuracy plot?
Yeah.
Here I was wondering how many data points was used. I mean, we don't have confidence intervals, but is it possible to zoom in to see that these instances that have improved is that?
Yeah. I have a few examples in one of the next slides, and in the paper we have dozens of them. So we were at the math learn principle. In the drop benchmark, the learn principle was perform calculations using the full precision available and only round as a final step, which apparently is a common mistake in this benchmark. In another benchmark called Boolean expressions, which is part of Big Bench Hard, the principle was double negation, as in not, cancels out and returns the original value, which also makes sense. In a benchmark called Snarks, the learn principle was sarcasm often involves saying the opposite of what is meant, and I'll show an example that uses this principle in a few slides. So here's an example from the math benchmark. The question is to evaluate this expression. The baselines answer the few-shot chain of thought. If I remember correctly, with the GPT-4 was incorrect. The model fails to simplify one of the steps. And in contrast, the learned principle in this case was it is crucial to accurately calculate the powers of a base in logarithm problems to correctly determine the exponent. Additionally, understanding the definition of a logarithm is key. The logarithm base b of a number x is the exponent to which b must be raised to get x, which makes sense. And indeed, using the same few-shot examples and the same model with the only difference of having this principle and a few other principles in the prompt, the model solved the problem correctly and simplified the final step correctly. Here's an example from the Boolean expressions benchmark, where the task is to simplify this Boolean expression of not, false and not false is. The baseline chain of thought reaches a state where the expression is not false and simplifies that to not true, which is a mistake, and reaches the final incorrect answer. And in contrast, one of the principles that was learned in the leap case was double negation, as in not cancels out and returns the original value. And indeed, using the same few-shot examples, everything was the same, except that we included these principles as well. The model reaches the same state of not false and simplifies that to false. And eventually, the final answer is correct. Here's the example from the SNARKs benchmark that I told you about. The question here is, which statement is sarcastic? Options: A, it's not our job to fund education. It should be the government paying the maintenance to keep schools open. Or B, it's not our job to fund education. It should be the kids paying the maintenance to keep schools open. And the question is, which of them is sarcastic? The baseline chain of thought response is that the sarcastic option is A, because the statement is not typically used sarcastically, so it can be seen as a genuine belief or opinion. In contrast, the principle that was learned in our case was that sarcasm often involves saying the opposite of what is meant, so paying attention to the incongruity between the literal meaning of the words and the intended meaning can help in accurately identifying sarcasm. And again, using the same, everything was the same except that we included these principles as well. The same model had reached a conclusion that that statement B contradicts the generally accepted understanding that children should not be burdened with the financial responsibility of maintaining school. And the presence of such a contradiction in B suggests that it contains a taste of irony and sarcasm, so their sarcastic option is B. Yeah.
You know, it seems to me that possibly this is overfitting to idiosyncrasies of the data set. Like every data set is done by a certain group of people, and this rule may not apply. So it's too low level. A lot of the rules.
Yeah, I agree.
We're seeing 1% improvement in engine.
Right. The learned principles are quite specific to the bench, fairly low level, and they're specific to the benchmark, like transferring principles that were learned on this SNARKs benchmark and transferring them to a math benchmark will probably be useless. The learned principles are domains.
No. It's obviously for the benchmark, but I'm saying for that particular, the way the three people who made the benchmark.
I see. Right, and in this case, I think that it depends a lot on the kind of internal variety of the questions inside the benchmark. In benchmarks where most of the questions are similar, or they have the same kind of principle that would solve them or fix them, applying this approach would be easier, right?
What I'm saying is SNARK can be done in many ways, right? And then these three people who created the data set have a certain way of doing it, and so it's sort of taking from the pattern.
Possibly.
You only have 1% or something in many ways.
Possibly, yeah.
Students overfitting to the types of exams a particular professor writes.
Yeah.
Right, those three people. Yeah. Right, yeah.
So in some cases, this can lead to only 1% improvement, but in other cases, this kind of pattern can be exploited to get an even higher gains.
Yeah, too low level.
Yeah, they are low level. I just think that if the entire test set is composed of questions that this low level principle can help identifying, this can work in your favor as well.
Yes, because the test set was created by the same people.
Yeah. If there's a professor who makes the same tests or similar tests every year, it's easier to exploit that professor's patterns. Yeah.
And that's what the training set is. Yeah.
Yes, please.
So how many low-level principles did you extract and fit to the model?
I think that if I remember correctly, something like 30. And if we used the high-level principles, we asked the model to summarize them into 8. These are just numbers that we came up with. We didn't do any further.
So now my second question is, have you looked at like whether there is like 4 or 5 of such principles that are very useful, and maybe some of the other ones are not that useful, like identifying like.
Yes. If you look at the set of principles for a certain benchmark in a certain model, some of them, at least to human eyes, seem to be more useful. We can never know which of them. Like we can know. We we can do ablation studies and remove each of them, and try all the possible subsets of principles and see which subset is the most beneficial. We didn't do that. But if you look at them, some of them do look more useful and some of them do look more trivial. I don't know if the ones that I identify as useful are actually useful to the model.
Sorry to ask.
Sure, go ahead.
Now, if you generate the principles, let's say using Gemini, then use them on GPT-4 or vice versa, are they useful for each other? Like, do they?
Yeah, great question.
Imagine they make mistakes in different ways.
Right. Usually they are still useful. We didn't report the numbers exactly. So I repeat the question. The question is what happens when you learn principles with Gemini, for example, and then provide these principles to GPT-4. We didn't report those numbers because we didn't know what to compare them to. It's unclear whether if you have an improvement, whether the improvement is due to the better principles, better application of principles, or just due to the kind of variety that you introduce by kind of mixing two different LLMs that have different patterns. But generally, yes, among the strongest models of Gemini, GPT-4, and sometimes GPT 3.5, usually the principles for the same task were transferable. My next slide is about whether this works with open source models, which is a question that we were asked a lot. And we tried this with Llama 270B. This was before Llama 3 came out. With Llama 270B, Leap didn't work at all. So Llama 2 did not benefit from this process of learning principles at all. So we wanted to see, as Ahmad suggested, whether the reason is that Llama 2 learned like less useful principles, or whether it learned useful principles but did not manage to apply them to the test set well. So just using Llama 270B in both steps of learning principles and applying them did not work at all. So we tried to take Gemini's principles and giving them to Llama 2 to apply them. This did not help. And the other alternative of learning principles using Llama 2 and providing them for Gemini for inference slightly helped, but not as well as using Gemini for both steps. So overall, my conclusion, at least, and as you suggest, is that there are two different abilities here. One ability is to learn the principles by looking at correct and incorrect examples and learning the difference between them. That's one ability that LLMs need in order to leverage this approach. The other ability is kind of an instruction following ability, where given a principle, whether the LLM can actually apply it and detect the cases where this principle is relevant and actually apply the principle and produce better results. I believe that these are two general abilities that accidentally come together in these cases. The strongest model, like Gemini and GPT-4, roughly had these two abilities, and Llama 2 was slightly better in learning principles, but worse in applying them. But it's just one experiment. I'm not sure that we can tell which ability is like more difficult or something like that. But yeah, I agree that it's important to remember that these are two abilities. Remember that I told you that the self-refine, where the model does not use any few-shot examples, just refines its own generated examples, does not work for reasoning. Last week, a model called Reflection 70B was announced, and the main idea in that model was that it can generate an answer for a question and then go into a reflection mode where the model actually generates the token reflection and end of reflection. And within those two tokens, the model generates a kind of a reflection of the previous answer. And actually can correct itself and say, initially the question was how many R's are there in the word strawberry? The model said that there are 2 R's, and then in the reflection state, the model corrected itself and said that actually there are 3 R's. So when I saw this tweet and made these slides last week, I was about to tell you that maybe I was wrong, and my initial statement that self-correction does not improve reasoning is wrong, and maybe with specific training, models can self-correct themselves, and maybe it is possible. However, last night there were people checked the results and tried to reproduce the answers, and there were some serious concerns about the validity of the results and the of the initial reflection 70B model. I'm not judging and I haven't checked, but some people called it fraud. So maybe self-correction is not working, and maybe we should benefit from principles. So to summarize, LLMs can leverage negative examples if we have the ground truth to contrast them with and express the learned principles explicitly. The basic insight is that principles that were learned on the 3 few given examples transfer to the test set of unseen examples. This is, as I mentioned, a one-time process of learning the principles of about 30 LLM queries. So the cost is very bounded, and then the same principles can be used for the entire test set. And this leads to 7.5% improvement in drop, 3.3% in hotpot QA, 1% in GSM 8K and math, and sometimes it doesn't help at all. We're not sure why. And that's it. Are there any questions? Thank you. Yeah.
Thank you for the talk. It's really elegant approach. So there are 2 parts which improve the final results. One are negative examples prompted to being generated. The other are the principles. So I wonder how much of the performance gain can be attributed to negative examples. For example, like quantitatively, I could imagine describe the task like GMS 8K is a grade school math problem. Please generate 8 principles to help you. Maybe use that as a baseline. Qualitatively, are there evidence that some negative examples, when provided, influence the final high-level principles, which makes similar problems solved more accurately?
Yeah, I agree. It's a good point. We haven't tested that, but I'll repeat what you're saying. You're saying that basically another baseline to check would be to just provide only positive examples, as people usually do, but also ask the model to generate like 8 principles before solving the test questions. I agree. Yeah, good point. We haven't tried that. Any other questions? Yeah.
So if you purposely have very different examples that making it very hard to come up with any general principle, what will happen?
If you purposely pick very different example? Yeah. So I don't think that necessarily it will be impossible to generate the high-level principles. One of the some of the goals of the high-level principles is just to deduplicate and abstract and summarize. So there are many cases where the models generate the same principle many times, and I think that in that case, even if the low-level principles are very different from each other, the high-level principles would still be meaningful, at least for humans, at least from what I've seen. The principles do look useful because at the worst case, they are just abstracted or rephrased with more high-level words that do not refer specifically to any particular example. However, there are many tasks in which the high-level principles did not help at all. So maybe these are the cases where the variance of the few-shot examples was, as you suggest, high, and the high-level principles were not not useful or not better than the low-level principles.
I guess I'm saying that it's a design question, right? How do you design this few shot example so that to achieve whatever you want to achieve? Right now, it's just try and error.
Okay, so yeah, there are two questions here. In order to actually use this, I think that the principles should cover as much as possible from the test set and be varied and be different from each other, and I think that if they would be the most representative of the test set, that would be best. However, for writing a paper, we didn't want to do any of that, so we could claim that we didn't do anything and didn't design anything and didn't manually do anything. It just works. So I agree, there are some things that you are some scientific questions that are important, but you're kind of not do not want to present them in a paper. So the bottom line is that we didn't try varying the few shot examples. In realistic settings, if I were to apply this to like a real problem, I would pick as varied examples as I can. Yeah.
But I think to Andre's point, there might be scope for kind of negative example mining. Like if you look at the probabilities, like if a mistake is high likelihood under the model, maybe that's something that we actually want to focus on for getting hooked out of.
Yeah, I definitely agree. I haven't thought about it, but it's a good point. I'll repeat the comment. The comment is that in the step where we take each of the labeled examples and sample different solutions and filter out the correct ones and keep only the incorrect ones, the point is that we should pick, if we can prioritize or pick some of the negative examples, we should prioritize negative examples that have a high probability, because these represent mistakes that are more likely to happen naturally. So they are more natural mistakes, right? Yeah, I agree. We haven't tried that, but it's a good point.
Man, this is just like in general a hard question, right? Like even with going with the student analogy, right? Like somehow extracting mistakes that students make that are kind of conceptually illuminating is very hard. Like most of the mistakes there's no general principle.
Yeah. Yeah.
Thank you again.
Thank you.